This video presents the use of infrared spectroscopy for the determination of the structures of organic compounds, and I'll give a brief background and theory as to how infrared spectroscopy works, and then I'll talk about structure determination in more detail. So first off, the most important information that we get from infrared spectroscopy in organic chemistry are the types of functional groups in a compound. So if you have an unknown compound or a compound that you just made and you want to know what functional groups are present, often the first thing you'll turn to is an infrared spectrum. And this takes advantage of the fact that different types of bonds absorb infrared light at different frequencies. And we'll talk about why that is right now, talking a little bit about the theory now. So covalent bonds, it turns out, are like springs. So if we look at a simple diatomic molecule, like hydrogen chloride, for example, we can think of the covalent bond between the two atoms as a spring. That is, it can stretch, and it can bend, and it can vibrate just like a spring. So if we were to plot the potential energy of a bond, so this is the potential energy versus the distance between the two bonded atoms, we see a potential energy well that looks something like this. So as the atoms are very close together, we start with very high potential energy. As they come farther and farther apart, we descend into a well that it gradually rises until the two atoms are essentially no longer in a bond. And so out here, the two atoms are very far apart. They're no longer bonded. And so they have the potential energies of the individual atoms. As the bond forms, there's a decline in the potential energy until it reaches a minimum. And this minimum right here is the ideal distance, the lowest energy distance between the two bonded atoms. So this is where the two bonded atoms, the distance where they are most stable. And as the two atoms get closer and closer together, we start to experience the repulsion between the two positively charged nuclei. So they're very close together here, and the nuclei are repulsing. So now it turns out that everything at this level is quantized. We're in the level of quantum mechanics now. And so the curve isn't really smooth like this. That is, there are only certain allowed energy states that we can draw as little lines on the curve. So these are energy levels. And these are known as vibrational energy levels because as a molecule accesses these or moves from one energy level to another, it's vibrating with a different frequency and a different distance between the two bonded atoms. So the vibrational distance here is greater than the vibrational distance here, so that atoms can get farther apart in this vibrational energy state. You got more of a stretched spring here than in this vibrational energy state. And this is a higher energy vibrational state. Now, the gaps between these energy states, for example, that distance right there, or this distance right here, these gaps correspond, these are energy levels, so there's differences in energy between these energy levels. So the energy differences for these gaps, maybe I should do this in green, correspond, as all energy level differences do at this level, to some frequency, there's frequency, of electromagnetic radiation. And it turns out this frequency is in the infrared region of the electromagnetic spectrum. So these are IR frequencies. So in other words, if you shine IR light on covalent bonds, it causes the bonds to vibrate. And different wavelengths, higher energy wavelengths or frequencies of infrared light can cause the bonds to vibrate with greater energy, higher frequencies, and correspondingly greater interatomic distances. And it's critical to understand that different bonds have different vibrational energy states. And so there's different gaps between these energy states when you have different bonded atoms. And those different gaps correspond to different frequencies of absorbed light. So different bonds have different energy levels, different vibrational energy states, which correspond to different frequencies of infrared light that can be absorbed. And that's the basic the basic principle behind infrared spectroscopy. Now, a diatomic molecule like hydrogen chloride is pretty simple. There's not too many ways this thing can vibrate. It can stretch. This is a simple stretch here, the two atoms moving closer together and farther apart. As molecules get more complicated, however, there are different types of vibrational frequencies, vibrational modes that are available. And that different types of vibrational modes, the more vibrational modes there are, the more different wavelengths of light that can be absorbed, of infrared light that can be absorbed. And that's what I show down below in the next section. So more complex molecules have more vibrational modes. So we'll start with the simplest one that we were just looking at, and that was a simple stretch. The stretching frequencies are the most important. The stretching modes are the most important in infrared spectroscopy. So again, we had hydrogen chloride. And the simple stretch is just the spring stretching and compressing as the two atoms get closer and farther apart. When you've got more than two atoms, though, and again, the more complicated the molecule, that is, the more atoms and bonds you have, the more different modes you have. So if we have, for example, in a water molecule, we've got three atoms, and when you've got more than two bonds to the same bonded to the same atom, you can have what are known as coupled vibrations. And so one type of coupled vibration is known as a symmetric stretch. So in a symmetric stretch, both atoms are moving with the same frequency in the same direction. So both of these hydrogen-oxygen bonds would be compressing in the same direction at the same time, and they would both rebound out, stretching at the same time in the other direction. So that's a symmetrical stretch. There's also an asymmetrical stretch for this type of bonding arrangement. So you see this in sp3 hybridized carbons where you have hydrogens coming off, say, methylene groups as well. So the asymmetric stretch is when one bond is lengthening and the other is compressing. So this one will lengthen as this one compresses, and then the reverse happens. That one will compress while this one lengthens. So that's an asymmetric stretch. So those are known as coupled vibrations. And there aren't just stretching vibrations available to molecules. There are also bending vibrations, which are not as important in infrared spectroscopy, but they are certainly, you can certainly see them in an infrared spectrum. So I'll give one or two examples of a bending. So if you had a methylene group, for example, water would do this as well. The two hydrogens can scissor back and forth. So just like a pair of scissors, they move closer together and they move farther apart. So this is known as scissoring. And scissoring is also known as out-of-plane or in-plane bending. I'll give one more example here. You can also have out-of-plane bending. So imagine, for example, that this particular hydrogen, the plus sign means it's coming out in our direction, it's bending out towards us. This hydrogen at the same time would be bending back away from us. So these two hydrogens are bending, one's coming up out of the plane, one's going back, and that's known as out-of-plane bending. Now the more bonds and atoms you have in a molecule, the more bending and stretching and coupled vibrations that you can have, and the more complicated the spectra tend to become. So there can be many of these things. These are just several examples. The most important ones for our purposes in most cases in infrared spectroscopy are the stretching frequencies, however. And so most of the ones that we'll be seeing when we determine the structures of compounds will be simple stretches. Next, I want to briefly discuss how infrared light is absorbed by bonds, because this has important implications for infrared spectroscopy and how we interpret infrared spectra. So what happens, you have to recall, of course, that infrared light is electromagnetic energy, which we can represent as electromagnetic waves. So here's the incoming wave of infrared light. And polar bonds have dipoles. So if we look at a carbonyl bond, for example, we know that the oxygen is more electronegative, so it's got a partially negative charge, and the carbon is partially positive relative to the oxygen. And what happens when these electromagnetic waves interact with these dipoles is the dipoles start to rhythmically vibrate. So you can think of this as an electric field that interacts with this charge difference here, this dipole. And as the electromagnetic energy, the IR light of proper frequency, interacts with this dipole, it causes the dipole to vibrate. And so I can represent that with these arrows here. So as the infrared energy is absorbed, the dipole begins to vibrate. And that is really all you need to know about how this light is absorbed. What's critical here is that there must be a dipole. So for IR light to be absorbed by a bond, there must be a dipole. So if we look at a couple of examples here, we could take a look at a common diatomic molecule like nitrogen, for example. Nitrogen has no dipole and therefore is not IR active. And so if you take an infrared spectrum of nitrogen, you don't see anything. Contrast that to carbon dioxide. So we know that the carbonyl bonds in carbon dioxide are polar, and therefore there are vibrational states, modes, that are IR active. Now it turns out that there's an asymmetric coupled mode here. So when, say, both of these oxygens push inward and then go back outward, that's a symmetric vibrational mode. That's not IR active. However, there's also an asymmetric mode present, where both of the oxygens are vibrating in the same direction. So if both are going out in this direction, that's an asymmetric mode, and that is IR active. So carbon dioxide you can see in an infrared spectrum. And one of the interesting things about this is is related to the greenhouse effect. Nitrogen is not a greenhouse gas because it does not absorb IR light. The greenhouse effect is predominantly due to the absorbance of gases in the atmosphere. Gases in the atmosphere will absorb IR light that's re-reflected from the surface of the Earth. Normally that light goes right out back into the outer space, and so the Earth cools as the Earth emits this infrared light into space. But if you have lots of greenhouse gases like carbon dioxide present, the carbon dioxide and the greenhouse gases with these dipoles will absorb some of that infrared light and re-reflect it back down to the surface. So for that reason, maybe I should do that in red, nitrogen is not a greenhouse gas. But carbon dioxide is a greenhouse gas because it is IR active, it absorbs light and re-reflects this thermal IR radiation back down towards the surface of the Earth. So, for our immediate purposes, the reason this is really important to understand is that symmetrical bonds like nitrogen are not going to appear in our infrared spectra. So for example, I should probably write that down too. So for example, if you have a terminal alkyne, alkynes are IR active. A terminal alkyne like this is IR active. There is a very slight dipole. But a symmetrical alkyne is not IR active. So symmetrical bonds with no dipoles, symmetrical alkynes for example, will not appear in our infrared spectrum. An unsymmetrical alkyne will, because it does have a dipole. So that's an important thing to bear in mind when you're looking at using infrared spectroscopy for structure determination. The bonds must have dipoles, even very slight ones, and therefore they cannot be symmetrical. So now there's just a couple more things to talk about with regard to the theory of infrared spectroscopy. So first note that the intensity of an absorption in an IR spectrum is proportional to the bond dipole. So very simply, in other words, if you have a very strong dipole, big electronegativity difference and long bond between two bonded atoms, as you see, for example, in a carbonyl bond, this will give you a more intense absorbance or absorption than, say, a less polar bond, for example, a carbon-chlorine bond. And we'll see in the next section what that's going to mean, what that's going to look like in an infrared spectrum, is we're actually measuring percent transmittance. So a carbonyl bond will have much less transmitted light and have a stronger absorbance than, say, a carbon-chlorine bond will. So this might be your carbonyl stretch, and this might be your carbon-chlorine stretch. And we'll see more examples of this in the next section. So finally, and most importantly from the viewpoint of structure determination, the frequency of the absorption of infrared light is proportional to the bond strength and inversely proportional to the masses of the bonded atoms. So for example, or to elaborate a little bit here, frequency, nu, is proportional to the square root of the force constant K of the bond over the masses of the bonded atoms. So again, K is the force constant of the bond. So what does that mean? Springs also have force constants. So if you have two bonded atoms, thinking again as the bond of the bond is a spring, so this is atom A, and this is atom B. The stiffer this spring, so the harder it is to push, to compress, or to pull apart, the greater the force constant. So greater force constants give greater vibrational frequencies and greater frequencies of infrared light absorbed. M corresponds to the masses of the bonded atoms. So since mass is inversely proportional to frequency, lighter atoms like hydrogen will give greater frequencies, greater vibrational frequencies than heavier atoms. And with that, we're now ready to look in more detail at the actual use of infrared spectroscopy for the determination of the functional groups in a compound. So in learning to interpret infrared spectra, I'm going to begin with features of infrared spectra, and then I'll turn our attention to the specific frequencies at which different common functional groups are commonly found in infrared spectra. So here is an infrared spectrum of octane, which is fairly simple because there's really only one type of bond here that has a bond dipole, and there's the CH bonds. And so what we're seeing here, before I get into that, let's talk about the features of the spectrum. First, we're plotting, an IR spectrum is usually plotted percent transmittance, and that's simple. That's the amount of light that goes through a sample. So 100% is at the very top here. That means all the light's getting through. And as we scan along the different frequencies of infrared light, different functional groups, different types of bonds will absorb, so the percent transmittance will go way down. So this is a CH stretching frequency. And we expect the CH frequency to be pretty high. This is high frequency here in this direction because the hydrogen atom, recall, is very small. Remember, the smaller the atom, the frequency is inversely proportional to the masses of the bonded atoms. And since hydrogen is very small, we'd expect the hydrogen stretching frequencies to be fairly high, as we see here. So that's what wave number is referring to. So we got percent transmittance on the x-axis, wave number is on the y-axis. And wave number isn't exactly frequency. So that's the next thing I'm going to define, and we'll talk more about this particular spectrum and then look at some common functional groups. So first, wave number. Recall that frequency is defined as cycles per second. So the number of cycles of a wave that pass through a point in 1 second is the frequency. And this is often just simplified to 1 over seconds, or seconds to the minus 1. And that, of course, is equal to hertz. So all of those are simply the same units for frequency. Wave number is closely related, but not exactly the same thing. So wave number is defined, instead of cycles per second, as cycles or waves per centimeter. And this is often simply written as 1 over centimeters, or centimeters to the minus 1, or reciprocal centimeters. And so our units for wave number here are reciprocal centimeters. But wave number is very similar to frequency. And in fact, they're proportional, so the number of cycles per second is proportional to the numbers of cycles per centimeter. So wave number, which we'll symbolize with nu with a bar, is proportional to frequency, which is simply nu. So frequency is proportional to wave number. And so from this point on, if I'm referring to frequency, I'm really talking about wave number. So wave number, since wave number and frequency are proportional, I'll refer to the frequency of absorption of a particular bond or functional group. And I'm really talking about the wave number. So we see here that the range of wave numbers, frequencies, ranges from 400 reciprocal centimeters to about 500, all the way down to 400 in some IR spectrophotometers. And that corresponds to, that is, the IR region corresponds to, it's used in common infrared spectrometers, from about 2.5 times 10 to the minus 4th centimeters, and this is wavelength, to 2.5 times 10 to the minus 3rd centimeters. So that's equal to our wavelength in centimeters. And as we see up above, we're talking about a range from 400 reciprocal centimeters down to about 500 or 400. So 2.5 times 10 to the minus 4 centimeters corresponds to about a wave number of 4,000, and this corresponds to a wave number of about 400. So that's the typical region we see in infrared spectra. So now let's briefly look at the simple spectrum of octane. And so as I mentioned a moment ago, our CH stretch is at fairly high frequency because we've got these very small hydrogen atoms. And we don't see much else in the spectrum. Way down here below 1500, we're seeing CH bending frequencies, and note those aren't as strong. The bends aren't as strong as the stretching frequencies. And there's a rocking CH2 methylene frequency down and around 600 reciprocal centimeters. So the region below about 1500 centimeters is known as the fingerprint region. So I can highlight that. So this region where we see lots of bending and rocking and different types of vibrational frequencies is known as the fingerprint region. And the reason for that is this isn't so diagnostically useful, except for the fact that, as you would expect from the name, the fingerprint region is unique to each different type of compound. So you'll never see exactly the same fingerprint region in different compounds, because these different types of frequencies are highly dependent on the complicated or not so complicated structure of a molecule. Most of our information of the functional groups comes in the higher frequency regions beyond the fingerprint region, frequencies at wave numbers higher than the fingerprint region, as we're going to see as we move from one functional group to the next below. So we'll begin our journey of the common absorptions, IR absorptions of different functional groups with the CH carbon-hydrogen stretching frequencies. And we've already seen an example of that above, right here. And as I mentioned, this of course is at fairly high frequency because of the small size, the small mass of the hydrogen atom. And so interestingly, the hybridization of the carbon bearing the hydrogen that's being observed affects the CH stretching frequency. And so, as we see above, the carbon-hydrogen stretching frequency for an sp3 hybridized carbon ranges from about 3,000 to about 2,840. So just regular sp3 hybridized carbon bonded to hydrogen has a CH stretching frequency below about 3,000 reciprocal centimeters. As we go to sp2, the CH stretching frequency increases, and so with CH2 carbon bonded to hydrogen, we see frequencies above 3,000, so from about 3,000 to about 3,100. And it goes even higher with sp hybridized carbons, where we see stretching frequencies in the region of about 3,260. And so that would be, of course, for a terminal alkyne. And so what does that look like? For 1-hexene, we're going to see, in addition to the CH, the sp3 CH stretching frequencies, so that doesn't change very much, at about 3080 in this case, we see a moderate peak for the sp2 hybridized. So we're talking about, maybe I should color code these. So this peak right here corresponds to the CH stretching frequencies for the vinylic hydrogen, carbon-hydrogen bonds. And there's also a couple new features farther at lower frequencies. We've got a peak right around 6042 that corresponds to the alkene stretch. So there's a stretch of the carbon-carbon double bond at about 1642 here, and there are a couple of other small peaks that we didn't see in our octane. But note, the main thing we're pointing out here is that we have a higher frequency CH stretch for the carbons, the hydrogens bonded to the sp2 hybridized carbons. Now if we look at 1-hexene, again recall that we have an even higher frequency CH stretching. And so we see a fairly strong, actually a moderate peak at about 3311. And so the sp hybridized carbon hydrogen stretching frequency is the highest of all of these. Another important feature of this spectrum is the carbon-carbon triple bond stretching frequency, which is about 2210 in this case. So we see a peak right around 2210. These are usually around 2500, and this is for the asymmetrical carbon-carbon triple bond stretching, the alkyne stretching frequency. And this is really diagnostic for triple bonds. You almost never see anything resonant or absorbing in this region of about 2250 except for triple bonds. And so I think that's the next one I'll briefly talk about, since I've already introduced that. So as we saw just a moment ago, unsymmetrical alkynes, and we're talking about the alkyne stretching frequency, absorb right around in the region of about 2260 to 2100, which is right about what we saw for our hexine above. So, And the strength of the absorbance is generally weak to moderate. Okay, so we see a pretty strong CH, and the reason this is so strong is there's so many of these carbon-hydrogen bonds. So for the one alkyne there, this is weak to moderate. W meaning weak and M meaning moderate. Remember the intensity of the absorbance. I should probably point that out too on the spectrum. So the intensity is the percent transmittance. So when there's a low percent transmittance, this is an intense absorbance. And if it's a higher percent transmittance, it's a weaker. So we generally classify these as weak, moderate, or strong. So this would be strong, this would be weak, and these would be moderate. So, and of course, recall from earlier that the intensity is a function of how polar the bond is, unless you have a whole lot of one type of bond, as we're seeing with these CH bonds. One more thing I should reinforce about the alkynes is that symmetrical alkynes are not IR active. So there's one other type of triple bond you'll see in common organic molecules, and those are nitriles. And what's convenient about those is they absorb in that same characteristic region, almost exactly the same. So nitriles absorb in the region of about 2260 to about 2240. And they are also weak to moderate. The next functional group we'll look at are alcohols and the OH stretching frequency, which is really diagnostic in infrared spectra. So if you're thinking about an alcohol, one of the first places to look, maybe the first place to look, is an infrared spectrum. So to begin with, most alcohols are hydrogen bonded. So if an alcohol is hydrogen bonded, the OH stretching frequency is usually in the range of about 3550 to about 3200. And it's really very characteristic. It's not just the frequency and the intensity of the absorbance, and this is usually strong, but it's also the shape. As we learn, as you get deeper into spectroscopy, pattern recognition is really, really important. And so let's take a look at what an OH, a hydrogen bonded OH, looks like. So we see for a simple hydrogen bonded alcohol like cyclohexanol is this enormous, strong, broad OH stretching frequency that centers right around 3300. And so if you see something like this, you've got an alcohol. And almost all alcohols are hydrogen bonded. One of the feature of alcohol spectra is the carbon-oxygen single bond. That appears in the fingerprint region, and that's right around 1100. So, and that's a fairly strong. That can move around a little bit. So that's the CO stretching frequency, the carbon-oxygen single bond. There is another possibility with an alcohol, and that's a non-hydrogen bonded alcohol. And that's unusual. But if you see a non-hydrogen bonded alcohol, those tend to absorb at slightly higher frequencies in the range of about 3650 to about 3584. And those are sharper and usually not quite as intense. So you'll see a peak right around this area. So a little bit above 3500 down to just a little bit below 30, well, just a little bit, usually a little bit above 3500, and it's sharper. So I'll write that below. It's unusual, but it's possible. So closely related to alcohols are amines. They also hydrogen bond, and they also absorb in a very similar region. So simple primary amines absorb in the region, and with primary amines you get two absorptions that are sharper and not as strong as alcohols are. And so those are in the range of about 3500 to about 3400. With secondary amines, there's only one absorption because there's only one nitrogen-hydrogen bond. And that's generally in the region just about the same, about 3550 to about 3310. And so I will also show you briefly what that looks like. So from this point forward, I'll ignore the fingerprint region since most of the information about the functional groups is at higher frequencies. And this is our primary amino stretching frequency. So this is two different NH bonds, and you see two different absorbances here in the range of about 3300. They're actually at 3360 and 3280, these two. So we typically see two rather weak absorbances, sometimes moderate, in this region for primary amines. With secondary amines, which just has one nitrogen bond, you only see one peak here. So, for example, for NN-dipropylamine, which is a secondary amine, we see a single absorption around 3290, right around 3300. So that's what you can look for if you suspect amino groups, primary or secondary amino groups in your molecule. So now we turn our attention to the final and maybe the most important of the functional groups that we'll be going over, and that is the carbonyl group. So we'll begin with aliphatic ketones, of which acetone is an example. And acetone has a carbonyl stretching frequency of about 1715. And so to look at what that looks like, and these are very strong, this is really diagnostic for carbonyls. You can see something around 1700, a strong peak around 1700, you can pretty much bet you have a carbonyl in the compound. So let's take a look at what that looks like. So the carbonyl stretching frequency in 2-pentanone is right around, it's very close to 1715, it's 1725, so just slightly higher frequency than an acetone. And it's very strong and looks something like that. So that's your C-carbonyl C-double bond oxygen stretch. And that's pretty typical. Ketones and aldehydes look just like this, as do most carboxylic acids, esters, and amides. You have a strong peak in the region of 1700, but there are slight differences between them, and I'll talk about each of those below. So the second one I'll mention is an aliphatic aldehyde. And so aliphatic aldehydes, for example, acetaldehyde, absorb in a similar region. Acetaldehyde is about 1730, and it looks pretty similar, very similar to what we saw for ketones. Next, we'll look at aliphatic esters. Aliphatic means that there are no double or triple bonds near the carbonyl. And so typically what you'll see for an ester is esters absorb at slightly higher frequencies than do aldehydes or ketones. And so esters you'll usually see in the region of about 1750 to about 1735. Similarly, amides absorb at lower frequencies. And there's a reason for that. And that is you have a pair of resonance forms in amides that lengthens and weakens the carbonyl bond. So this second resonance form has a single bond between the carbon and the oxygen. And so because of this, because you have this resonance form contributes to the resonance hybrid where you have a weaker single bond between the carbon and the oxygen and the carbonyl, we see a stretching frequency in amides of around 1690. That's lower frequency. The other thing to be aware of in amides is if you have a primary or a secondary amide, that is So this would be a primary amide. This is going to be similar to an amine, not exactly the same. So a primary amide, you're going to see an amine-like absorption, and you'll see two absorptions in the region of 3350 to 3180. So that's similar to amines. If you have a secondary amide, you'll see just one absorption in that same region. So bear in mind, if you have hydrogens on the amide nitrogen, you see amine-like absorptions in addition to the carbonyl stretching frequency at 1690. Carboxylic acids are particularly diagnostic, so much so that I'll demonstrate what that looks like on our spectrum above. So for a carboxylic acid, we have a carbonyl stretching frequency. And again, with carboxylic acids are typically hydrogen bonded. So, and that's normally what you see. So the carbonyl stretching frequency of a carboxylic acid, if it's hydrogen bonded, is about 1710. Again, these are for aliphatic carboxylic acids. If it's not H-bonded, the carbonyl stretch is at higher frequency and it's sharper. So this is this is about 1760 if it's not, but this is unusual. So this is what you normally see. And of course there's something else you have to look for, and that is the OH stretching frequency in a carboxylic acid, which you'd expect to be similar to an alcohol, but it actually is quite a bit different. It's enormous. And so these are all strong, these carbonyl stretching frequencies. This is an enormous, it's like a mountain. And it stretches in the region of about, it's the lower frequency than alcohols. It stretches in the region of about 3,300 to about 2,500 if it's hydrogen bonded, which they normally are. So let's take a look at what that looks like. So here we have a spectrum of pentanoic acid, and again I've ignored the fingerprint region, so this isn't accurate here. And we see our strong carbonyl stretching frequency right around where we'd expect it. That's about 1711. Usually we see them right around 1710. But notice the OH stretch. This is much different than alcohol. Remember that an alcohol is very strong and pretty broad in this region right here. With an hydrogen-bonded carboxylic acid OH group, we see this enormous mountain-like thing. The only thing that resembles this in any other type of functional group would be in an ammonium ion or an aminium ion, where we've got a nitrogen bonded to positively charged nitrogen. You see something like this. But generally, if you see a carbonyl with this giant mountain, and we see the CH stretching frequencies, the CH stretch is poking out of the OH mountain here, then this is really diagnostic for a carboxylic acid. So this is what hydrogen bonded carboxylic acids look like, and they're almost always hydrogen bonded. They usually exist as a hydrogen bonded dimer. So we have one more thing to talk about with regard to carbonyls, and then you're ready to begin using infrared spectroscopy to solve for the structures of organic molecules. It turns out that all of the different carbonyls and carbonyls that we've looked at, all these functional groups we've looked at this point, have been aliphatic. And the reason I specified that is because when there's an unsaturation in conjugation or in resonance with the carbonyl group, that changes the frequency of the absorption. So what we're talking about now, finally, are alpha-beta unsaturated carbonyls. So alpha-beta unsaturation reduces the frequency of the carbonyl absorption. The reason for this is the same as the reason that I gave for the reduction in the stretching frequency for amides above. So if we review that briefly. In amides, we have this resonance form here that lengthens and weakens the carbonyl oxygen bond in the carbonyl group. We see the same thing happening with alpha-beta unsaturation. So in other words, if we have an alpha-beta unsaturated ketone, this exists as a pair of resonance forms where this pi bond can move here and this can move on to the oxygen, giving us a resonance form where we have a lot of single bond character in the carbonyl-carbon-oxygen bond. And so this is going to reduce the frequency of the absorption of the carbonyl-oxygen bond, of the carbonyl stretching frequency in alpha-beta unsaturated aldehydes and ketones, and carbonyls generally. So what I mean by alpha-beta unsaturation is you have a double or a triple bond, or a benzene ring, for example, in conjugation with the carbonyl. So this is the alpha, this is the alpha carbon, and this is the beta carbon. And so we have an unsaturation, a double bond, a pair of pi electrons, alpha and beta, to the carbonyl carbon. So let's take a look and see what that does to our absorption frequencies. And so for this particular compound, this simple alpha-beta unsaturated ketone, our absorption frequency is 1685, the carbonyl absorption. And compare that to acetone, which is aliphatic, and that, of course, we saw earlier, 1715. We see the same thing for benzylic carbonyls. So if you look at acetophenone, the carbonyl stretching frequency is about 1683 versus, again, 1715 for the non-alpha-beta unsaturated acetone. And with that, those are probably the most important functional groups in more detail than you probably need to know. But with this, you should be able to begin to apply infrared spectroscopy to the structure determination of organic compounds. And as always, if you have any questions, please let me know.